Okay, then I'm back, and I now plan to take a look at exercise 1.6. And the equation here is ut plus ux equal to u. So, and then we should also add some initial data, phi x t equal to 0 is equal to phi of x. So when we look at this equation, we see that before we start doing any work, it can be wise to just make some, or try to build some intuitive understanding of what kind of equation do we have here. So first we see that we just have a very simple coefficient in front of the ux term. It's just 1. So it's velocity equal to 1 that rules when it comes to the transport mechanism. But then on the right hand side, we see that we have a source term, and this time it does not depend on x, neither t, but on the unknown solution u itself. So this is a new situation compared to equations we have looked at before. But let's just follow the general approach and see what happens. So we first solve for the characteristics. Dx dt equal to 1. And it's a starting point x0, and we directly find that then the characteristic is x of t is equal to t plus x0. So in the xt space, we have straight lines. Next, let's consider what happens along the characteristic. And to more precisely, we take the time derivative of u x of t t. And since we have done this many times or several times now, we see that we produce the equation itself, ux plus ut. But then, according to the equation, that should be equal to u x of t t. So when we compare what we have on the left-hand side here and the right, we see that we have an ODE equation, again, which can be solved by method of or by separation of variables. So on the left-hand side, we now have 1 over u du on the left-hand side, and on the right-hand side, we have just dt. And we integrate from 0 to t, and the corresponding integration with respect to u is phi x0, because that is what comes out when we consider u at time 0. And then we find the natural logarithm of u x of t minus logarithm of phi x0 equal to, and we integrate the integral on the right hand side, which gives us t. And this difference on the left hand side, that is the same as the logarithm of u x of t over phi. Like this. Then we are in a situation where we can apply the exponential function on both sides. And the exponential function of the logarithm function gives us u over phi x0. That is u x of t is equal to phi x0 multiplied by the exponential function. But then we have to see how we can make use of the characteristic to remove x0. But we know that x0 from the equation for the characteristics, x0 is equal to x of t minus t. So we get phi of x of t minus t multiplied by the exponential function. So the general solution where x and t are independent are now u x t is equal to phi x minus t multiplied by the exponential function t. And again, we can ask the question, where is the effect of the transport and where is the effect of the source term? And clearly, this part comes from solving ut plus ux equal to 0. This part must then come from the source term, u on the right hand side. So in this case, we see that we produce something that is a combination of transport and translation that takes place through this term, but then we multiply by the exponential function, which means that it will grow exponentially fast. Let's also do a verification of the solution. And first, for t equal to 0, we quickly find that that will give us phi of x. So that is okay. And we have to check the solution itself. Let's just recall what is it like. Phi of x minus t multiplied by et. So we compute the time derivative of u. And we see here that it involves a product of two functions that depends on t. So we have to use the product rule. So if we first take the derivative of phi plus phi x minus t, and then the time derivative of the exponential function. And further calculations here will give us phi prime x minus t. And then we take the time derivative of x minus t. And here we just, for the second term, we just take the time derivative of the exponential function. So that will give us nothing, just give us back. So this is the expression when we take the time derivative of u. Minus phi, and this is not an argument, this is multiplication with minus 1. Yep, okay. Let's compute ux. The spatial derivative of phi x minus t, et. And then this is easier because the exponential function depends on t, it goes on the outside, and we just have to take the derivative of phi x minus t. That will give us phi prime of x minus t multiplied by the time derivative, no, the spatial derivative of x minus t, which is just 1. Now we can plug into the equation ut plus ux is, in other words, equal to minus phi prime multiplied by et plus phi et plus et phi prime. And again, we see that this term will cancel with this. And what is left then is phi. And remember that the argument is x minus t, et. At first glance, this looks perhaps different, but then we look at the solution u, and we realize that this is just the expression for u. So we have proved that ut plus ux is equal to u. So then we know that this must be the correct solution. Any questions related to this exercise? If not, Perhaps I could ask a question. Are there any exercises you would like, you want me to go through? Or should I just stick to my plan then and take a look at exercise 1.10?
Sorry, can you just review 1.4, that stability?
1.4? Yeah, that's an exercise 1.4. Let me see. Perhaps I wonder if I should just, I cannot see if I have the exercise in front of me here, but this involves quite some calculations. Is that right? 1.4.
Yes.
Yeah.
Yes.
But okay, I think let me first take a look at this 1.10. So I'm sure that I have shown you a point or two related to that. And if there is time, I can start looking at this 1.4, or can publish a solution on Canvas.
Thank you.
Okay, let's continue with the exercise. First exercise 1.10. And this exercise deals with the solution of this diffusion equation. Now I use the variable v, but where we have a special initial data, vx at time equal to 0 is, and let me call this v0x, it involves this Heaviside function that jumps from 0 to 1 at x equal to 0. And then we have demonstrated that we have shown that we can compute an exact solution for this special case. And this is explained in detail in one of the lectures, that an expression for this solution is 1 over square root of pi, and then the integral from minus infinity up to x over 2 square root of t with argument exponential function of minus theta squared. And I also plotted, in the lecture, I also plotted the solution, and we saw how this initial jump, the solution after some time, it looked more like this. Well, this was not very nice. Okay, but the more important thing is that we clearly can study how this will smooth out this initial front, a diffusive smoothing effect. But then the problem here is to consider a slightly different equation, namely ut equal to epsilon uxx for epsilon, where epsilon is some parameter which is positive, but it's constant. And the initial data, is the same as the Heaviside function. Yeah, that is as for and the question is find a solution of star double star. And so what we have to understand then is how can we relate this problem, double star, to the model star, which we know the solution for. That must be the natural strategy here. Can we somehow remove this epsilon? Can we remove this epsilon, or can we transform this equation in such a way that this epsilon disappears? We have discussed this when we developed or constructed the solution of this heat equation. We talked about how we could transform the original problem into a by introducing new variables, we could transform one equation into another form. So let's try to apply this idea here. And what we would like to test is rescale time variable t. And there are, of course, many different ways we can rescale it, but let's just test if we introduce a new time t hat, which is time t multiplied by epsilon. Or that is the same as saying that t is this new time t hat over epsilon. And the plan now is to try to introduce or describe epsilon relatively this rescaled time t hat. What will happen then? So we want to consider we have u, x, t. That is the same as where u is the solution of double star. And that is the same as ux, and time t is now the same as t hat over epsilon. But that means that we can understand this as a function of x and this new time t hat. But then we have to rename this variable u and call it u tilde, for instance. And u tilde is understood as a function of x and t hat. And then the question is, what is the equation satisfied by this rescaled variable u tilde x t hat? But this is something we can compute, because we can just start with the time derivative of u, because we know the equation that u satisfies, namely equation double star. So let's see how we can use that fact. So the time derivative of u with respect to t or we can let me do it slightly different. We are looking for an equation for u tilde with respect to t hat. So that is the same as we are interested in the derivative of u the time derivative of u tilde, where the time now is t hat. But clearly, this is the same as the derivative with respect to t hat of u x of ux of let's see, u the time derivative of u tilde with respect to, yeah, that should be the same as the, okay. Let me see. How can we rewrite this? We want to use the relation between u tilde and u. So we first start with the time derivative of u tilde, but then we can clearly, according to this equation, that is the same as the time derivative t, the derivative of t hat with respect to u. But we see that u involves not t tilde, but t. So we use the chain rule to write this as the derivative with respect to t. And then but then we also have to multiply with the derivative of t with respect to t hat. Okay, that will give us u t multiplied by, and then we take the expression for t, and take the derivative with respect to t hat. But this will clearly give us just 1 over epsilon. So then we have converted the derivative of u tilde with respect to t hat. We have seen that that is the same as the derivative of u with respect to original time t multiplied by 1 over epsilon. But then we know the equation for u. So in particular, we know that ut is the same as epsilon u x x. We just use the equation. Multiplied by 1 over epsilon. That will give us u x x. But we are looking for an equation for expressed for u tilde, but we know that u tilde as a function of x and t hat is equal to u, and we see that both of them has the same spatial derivative, the spatial variable x. So clearly that is the same as u tilde x x, where it depends on x and t hat. So then we have found an equation u tilde is equal to u tilde x x. And this looks very nice because then we have observed that the effect of rescaling time is that the equation for u tilde contains no epsilon. So this rescaling helped to get rid of this dependence on epsilon. But so now we see that this u tilde is a solution of the first equation we started with here, since this contains no epsilon. But to conclude this, we have also to check that the initial data is the same. Let's check what is the initial data for u tilde. So we want to check what is u tilde as a function of x and t hat equal to 0. But clearly, since t hat is t multiplied by epsilon. So t hat is equal to 0 is the same as t equal to 0. And u tilde is equal to u. And this is the same as v0x. So we see that u tilde also shares the same initial condition. And then we can draw the conclusion. If uxt is a solution to or of the problem double star is equivalent to u tilde x t hat is a solution of the first problem star, which is without epsilon. And then we clearly have that we know that u tilde x t hat, we know the solution of star, namely this one. So we can make use of that and conclude that then this is equal to 1 over square root of I integral from 0 up to x over 2 square root, but now it is with respect to time t hat. Like this. But then in the next step, we can replace t hat by t. It is equal to t multiplied by epsilon. E minus theta squared. And u tilde is the same as u x t. So this is the solution in terms of x and t. So this is the solution of our second problem, because it now expressed the solution in terms of the variable x and x and t, which is involved here. And we also see how, as we should expect, that epsilon now will appear in the solution and have an impact on how this solution behaves. Okay, this is a nice illustration how one can solve a problem which is slightly different from the one where we know the exact solution. We can kind of build a bridge between the second problem and the unknown problem and the known problem by using by introducing a shift in the coordinates, in this case t. Okay, I will publish a solution both of this problem. So if you in addition to what I already have here. Yeah.
Yeah, I have a question. So in your solution, right, when you were integrating, you had boundaries of 0 to x all over 2 root of t and then epsilon. But if you scroll up, in the initial, if you scroll up, yeah, to the beginning,
yeah,
you had the lower boundary to be minus infinity.
Yeah.
So how did that change to 0?
Oh, that's a good question. This is a pure mistake from my side. That's a good comment. It should be minus, because we have not changed anything when it comes to x variable. It's the same x, so it should definitely not have an impact or effect. So thank you for your comment.
Thank you.
Okay, that's good that you saw this mistake. Well, I could perhaps ask a question here. Do you see, could we have solved this problem by introducing another shift or rescaling of variables?
Excuse me, sir.
Yeah.
I have a question. How we should understand we define t hat like t multiplied by epsilon? Why we didn't define it like t hat t over epsilon? I mean, how we should define the t hat?
Yeah, I would say that you just have to do that by trial and error, and you essentially just have to test. You could do as you suggest. If we set t hat equal to t over epsilon,
yeah,
we could try that, but by doing the same calculations, we would then end up with producing the derivative of this t hat u tilde x t hat. That would, when we do the same calculations here and we find that this is u t, but then we should take the time derivative, the derivative of t with respect to t hat, but that would produce yeah, that would produce epsilon, and then using the equation for u, we know that ut is equal to epsilon ux. So that will gives us epsilon squared uxx. And but since u and u tilde, they both have the same variable, that will be equal to epsilon squared u tilde xx. But what came out of this was then what came out of this rescaling was a new, we identify an equation for U tilde, but it just introduced another epsilon. So it didn't help us to link or transform this problem to a problem without epsilon. So it wouldn't help us. This would be correct, but it wouldn't help us to formulate the solution for U tilde.
Okay, thank you.
So, but of course, if you have not done this before, you just know that, okay, I will try to do, I can handle this problem by introducing some kind of rescaling. Then you would do as you have suggested. You just start with some kind of rescaling and then you test what happens. Here we see that it had the opposite effect. So, okay, then you understand that you have to use, introduce a t hat, which is the, where you multiply by epsilon. But there is another option. We could introduce x hat, which is x, for instance, well, one choice could be to multiply by epsilon or divide by epsilon. There are different choices. But what do you think? What do you think would work?
X over epsilon.
Okay, I'm not sure when I have to do the calculations, but one thing is sure: we should not use epsilon. We should use square root, because we have to do two derivations, to take the derivatives 2 times, and every time they will produce root of epsilon. So it will give us the product of that will give us epsilon. If we use epsilon, then yeah. So you see the point here, we have to use root of epsilon since we have 2 derivatives in x. And either you should multiply or you should divide. You have to do the calculations to check that. But that would also be, should at the end of the day, it should give the same answer. Okay. Then I see. Then we have had a look at 3 exercises. So this exercise 1.4, as I said, there is not time now to go through it, but I will publish a solution on Canvas so later today. So please take a look. Then I will stop this. Then we have ended this Zoom meeting, and I will start a new session 15 past 10, where the purpose is to work on exercises. So see you then.